designing a new breed of American armor when American engineers set out to create what would become the M4 Sherman. They faced a military landscape changing faster than any industrial system could keep up with. The armored forces of the United States were still shaped by interwar theories that placed maneuverability above protection and firepower. Yet the rapidly escalating conflict overseas made it clear that the nation required a tank fundamentally different from anything it had produced before. The challenge was not simply to design a battlefield weapon, but to construct an armored vehicle that the American manufacturing sector could reproduce on a scale unmatched by any other nation. This meant that every decision from armor layout to internal configuration had to meet the dual criteria of combat utility and industrial feasibility. Engineers re-examined nearly every aspect of American tank doctrine. They recognized that the new vehicle needed a fully rotating turret as the core of its fighting capability. Earlier designs, such as the M2 medium tank and the M3 Lee, suffered from split fire arrangements and limited gun traverse, making them increasingly outdated as tank warfare evolved. To correct these shortcomings, designers developed a large turret ring capable of supporting a more powerful cannon, improved optics, and enough crew space for efficient operation. Achieving this required a redesigned hull with a broader roof plate, reinforced structural ribs, and adequate interior volume for ammunition storage, radios, and access points. Armor configuration became another central engineering concern. Rather than simply thickening the steel plates, designers experimented with angling the frontal armor to increase the likelihood of deflecting incoming rounds. This tactic allowed the vehicle to maintain a reasonable weight while still offering improved protection. Engineers also placed great emphasis on crew survivability and internal ergonomics. They studied airflow, heat dissipation, ammunition, placement, and escape routes to ensure that the crew could fight effectively for long periods and exit quickly if the tank were disabled. Even seemingly minor elements, such as hatch dimensions and seating arrangements, were revisited with painstaking detail. One of the defining engineering challenges involved the tank's power plant. The United States did not possess a standardized tank engine suitable for the mass production envisioned for the new vehicle. SO engineers evaluated several alternatives. They tested radio aircraft engines, large welded diesel blocks, and multi-bank gasoline engines derived from automotive platforms. Each engine type had its own advantages and limitations, but the willingness to accept multiple solutions proved vital. By designing the tank to accommodate different propulsion systems, the Army ensured that engine shortages would not disrupt production schedules across multiple factories. Suspension development followed a similar philosophy. Engineers concluded that the tank needed a system durable enough to handle rough terrain, yet mechanically simple so that maintenance crews could perform quick repairs in combat zones. After extensive testing, they improved the vertical volute spring suspension, which provided a dependable balance between mobility, ease of servicing, and manufacturing practicality. This suspension design allowed factories to produce road wheels, bogies, and track components with consistent precision, ensuring interchangeability between vehicles built thousands of miles apart. Perhaps the most ambitious element of the Sherman's creation was the push for standardization. American industry required a tank that could be assembled not at one specialized facility, but across an entire network of factory steel mills, locomotive works, automobile plants, and heavy machine manufacturers. Engineers coordinated closely with industrial planners to ensure that every major component matched strict dimensional tolerances. This resulted in an armored vehicle that could be disassembled in the field, repaired with parts from distant facilities, and returned to action without waiting for custom replacements. By the time the final design matured, engineers had created a machine unlike any other tank in development at the time. It was not the heaviest, nor the most powerful, nor the most intimidating on paper. Instead, it embodied a deliberate engineering philosophy. Build a tank that could survive the battlefield, be repaired quickly, and be manufactured in extraordinary numbers. Through thoughtful design choices, meticulous attention to industrial compatibility, and an unwavering commitment to reliability, American engineers forged a new breed of armor one that would go on to become a symbol of logistical strength and mechanical dependability across the global theaters of war. The Industrial Revolution behind the tank, turning the Sherman from a finalized design into a mass-produced weapon, required an industrial transformation unprecedented in American history. Engineers were suddenly tasked with scaling a project far beyond the capacity of any single factory, and they had to accomplish it in an astonishingly short amount of time. The United States possessed immense manufacturing potential, but that potential had never been mobilized to create armored vehicles on an industrial scale. To meet the demands of a global conflict, engineers and industrial planners had to reimagine how heavy machinery could be built, pushing the nation's factories into an era of mechanized production that dwarfed anything that came before it. The first step in this transformation involved recruiting companies that had never produced military hardware. Automobile manufacturers, locomotive builders, steel foundries, and machinery firms were suddenly invited into a vast cooperative network. Their plants, originally designed for cars, engines, and commercial equipment, had to be reconfigured from the ground up. Engineers redesigned production floors, created new tool layouts, and built conveyor systems capable of supporting entire tank hulls. Conveyors that once carried sedans now moved armored steel plates, and stamping presses that had shaped car parts were refitted to form components weighing several hundred pounds. To ensure consistent results across dozens of factories, engineers created detailed manufacturing guides and dimensional standards that left no room for improvisation. Every turret ring, transmission, housing, and armor plate had to match exact specifications regardless of where it was produced. This demanded a level of precision unfamiliar to many plants transitioning from consumer goods to wartime machinery. Engineers developed specialized measuring tools, custom welding fixtures, and new machining procedures to guarantee that all parts remained interchangeable. Even minor deviations could jeopardize final assembly. So uniformity became a cornerstone of the production system. The construction of the tank's hulls and turrets required a dramatic leap in metallurgical engineering. Casting facilities had to adopt new molds and pouring techniques capable of shaping thick armor without internal imperfections. Engineers experimented with different alloy compositions, heat treating cycles, and stress relief processes to ensure that the steel remained strong yet workable. Welding teams needed new training programs to handle plates far thicker than anything they had ever encountered. To support them, engineers built reference manuals describing weld geometry, preheating requirements, and structural reinforcement methods. The introduction of standardized welding sequences ensured structural integrity while speeding up production. Material flow management became one of the most complex engineering obstacles. Factories needed a constant supply of steel, rubber, copper, optical glass, lubricants, electrical components, and precision machined parts. Engineers coordinated with transportation planners to build logistics pipelines that stretched across the country. Rail networks were reorganized to prioritize tank-related shipments, and warehouses were expanded to store massive quantities of raw materials. Engineers designed new packaging methods to protect delicate components such as gyroscopic stabilizers and sighting optics during long cross-country transport. Inside the factories, engineers refined assembly processes to eliminate bottlenecks. They introduced progressive workstations, each dedicated to a specific stage in the tank's development. Cutting and shaping armor plates, machining the turret ring, installing the drivetrain, wiring internal systems, and conducting functional testing. Subassembly areas built engines, transmissions, suspension units, and electrical harnesses before feeding them into the final assembly line. This modular approach allowed thousands of workers, many newly trained and unfamiliar with military equipment, to perform precise tasks with consistency. Quality control became an engineering discipline in itself. Inspectors used gauges, X-ray equipment, magnetic particle testing, and optical instruments to verify welds, armor thickness, and mechanical tolerances. Engineers documented every stage of production, recording measurements and performance results to identify areas needing improvement. Tanks could not leave the factory until they passed both mechanical trials and endurance tests. These evaluations revealed stress points, mechanical weaknesses, and assembly inconsistencies, prompting rapid engineering adjustments that improved subsequent production runs. The culmination of these efforts produced a manufacturing machine that operated with near-industrial choreography. Factories that had never built a single armored vehicle were now turning out Shermans at a rate unmatched anywhere in the world. At the peak of production, multiple plants collectively produced hundreds of tanks each month, transforming raw steel into fully operational armored vehicles with astonishing speed. This achievement represented far more than efficiency. It demonstrated a coordination between engineering, industry, and national infrastructure that reshaped American manufacturing for generations. The mass production of the Sherman was not merely a triumph of engineering. Design it was the embodiment of an industrial revolution. Engineers built a manufacturing ecosystem so effective that it became a decisive factor in global combat operations. Through standardization, logistical innovation, and relentless refinement of factory processes, the creation of the Sherman tank became a symbol of a nation. Its ability to mobilize its technological and industrial strengths on a scale that redefined modern warfare, armor, firepower, and the science of survivability, designing the Sherman for real-world combat required far more than shaping steel plates and fitting a cannon onto a rotating turret. Engineers had to balance the competing demands of armor protection, firepower, mobility, and internal crew safety, each a complex field of science in its own right. Instead of building the heaviest tank on the battlefield, American engineers aimed to create a machine that could endure long campaigns, operate reliably under harsh conditions, and survive the unpredictable threats of mechanized warfare. This engineering philosophy shaped every component of the Sherman, from the slope of its armor to the layout of ammunition racks. The Sherman's armor was a combination of rolled homogeneous steel and large cast sections, a method that allowed factories to manufacture complex shapes with consistent strength. Engineers discovered that a welling-owed armor plate could drastically increase its effective thickness without adding extra weight. As a result, the Sherman-esque Glaziesaur upper front hull was sloped at an angle designed to maximize deflection against incoming shells. Although the tank's armor was not intended to resist T-caliber German guns like those mounted on Panthers and Tigers, it provided reliable protection against the majority of battlefield threats, such as anti-tank guns, shrapnel, mines, and smaller caliber vehicles commonly encountered in mobile operations. Firepower was engineered with a similar philosophy of balance and adaptability. The original 75mm M3 cannon was selected because it offered both adequate anti-armor performance and excellent high-explosive capability. Combat data show that tank crews spent far more time firing at infantry positions, bunkers, and soft targets than dueling enemy armor. Engineers also incorporated one of the earliest practical gun stabilizers, allowing crews to fire with reasonable accuracy even while the tank moved slowly, on innovation that gave American forces a tactical edge during rapid advances. As the war progressed and enemy armor became more formidable, engineers responded by integrating a high-velocity 76mm gun in later Sherman variants. This upgrade required strengthening the turret, redesigning the recoil system, and recalibrating internal space without compromising the tank's existing balance. Other variants carried the 105mm howitzer for infantry support roles, demonstrating the platform's engineering flexibility and modularity. Survivability engineering became one of the most defining aspects of the Sherman's EVA. Early battlefield reports revealed that ammunition storage was a critical vulnerability, so engineers developed the wet stowage system. Shells were placed inside water-jacketed racks, designed to prevent rapid ignition when the hull was penetrated. This innovation reduced ammunition fires by more than 70%, dramatically increasing crew survival rates. Engineers also added improved fire suppression equipment, redesigned escape hatches, and optimized the crew compartment to make movement easier under stressful conditions. While critics often compare the Sherman unfavorably to heavier German designs, its engineering purpose was fundamentally different. Instead of maximizing armor thickness and gun size at all costs, American engineers focused on creating a survivable, maintainable, and versatile tank that could operate in vast numbers across diverse environments. Mobility, logistical efficiency, and reliable performance were engineered into every aspect of the Sherman. In the end, this combination of science-driven survivability and battlefield adaptability helped transform the Sherman into one of the most influential armored vehicles of World War II. Mobility engineering. How the Sherman conquered terrain. Mobility was one of the Sherman's most carefully engineered advantages, shaping the tank into a machine capable of crossing continents, pushing through urban ruins, climbing ridges, and advancing across mud-soaked fields without constant mechanical failure. From the earliest design stages, American engineers realized that battlefield success required more than armor thickness or gun caliber. A tank that could not maneuver reliably under fire or traverse long distances without breaking down would be more burden than asset. For this reason, mobility engineering became a central pillar of the Sherman's development, influencing its suspension, engine choices, drivetrain, and even logistical design. The Sherman's suspension system was one of its most defining mobility features. Early models used the vertical volute spring suspension V, a robust, and relatively simple configuration consisting of bogie units with paired road wheels supported by coil springs. Engineers selected this setup because it balanced durability with ease. Maintenance crews could replace bogies quickly in the field using only basic tools. Although VVS has limited ride smoothness compared to later systems, it gave the Sherman reliable off-road performance in environments ranging from North African deserts to the hedgerows of Normandy. As combat demands increased, engineers introduced the horizontal volute spring suspension This system distributed weight more efficiently and allowed the tank to use wider tracks, drastically improving flotation on soft ground. The HV's upgrade made the Sherman more stable, smoother to drive, and less prone to bogging down in mud or snow. These engineering advancements allowed late-war Shermans to keep pace with faster armored formations and provided crews with a noticeably more comfortable ride during long mechanized pushes. Track design played an equally important role in mobility engineering. Sherman tracks were built with modular links that allowed damaged sections to be replaced quickly, and many models featured chevron pattern track pads engineered to increase grip on slippery or uneven surfaces. Engineers tested track compositions to find the ideal balance between strength and flexibility, ensuring that the vehicle could endure thousands of miles of movement without catastrophic wear. This attention to detail made the Sherman far more mobile than many German tanks, which often suffered from fragile or overly complex track systems. Powertrain engineering was another key contributor to the Sherman's impressive mobility, because no single engine manufacturer could meet production demands. Engineers designed the tank to accept multiple engine types, including the Continental R9075 radio engine, the Ford GAA V8, and the Chrysler multi-bank engine. Each power plant delivered enough horsepower to move the 30-ton tank at competitive speeds. While their engineering emphasized reliability over raw performance, the transmission and differential were similarly designed to withstand constant stress during long operations, providing smooth gear transitions and dependable torque distribution. Logistical mobility, an often overlooked but essential aspect of warfare, was engineered into the Sherman from the ground up. American engineers ensured that components were easy to access, fluids could be replaced quickly, and common failures could be repaired in the field without requiring specialized technicians. Standardization across factories meant that replacement parts were interchangeable, allowing supply trucks to carry simplified inventories. This engineering foresight enabled Allied forces to keep Shermans running during rapid advances, long pursuits, and sustained campaigns across Europe, Italy, and the Pacific. The Sherman's mobility was not just physical, it was strategic. Its ability to traverse roads, fields, ruble, and forested landscapes allowed Allied commanders to plan operations with confidence that their armor would not collapse under mechanical strain. Compared to many Axis tanks, powerful but frequently immobilized by breakdowns, the Sherman represented a complete mobility system, fast to move, easy to repair, and engineered to endure. In the end, mobility engineering played a crucial role in why the Sherman became one of the most successful tanks of World War II. Its suspension, powertrain, track systems, and logistical design allowed it to remain constantly in motion, supporting infantry, spearheading offensives, and maintaining pressure on enemy lines. The Sherman conquered terrain not by brute force, but through precision engineering and reliability qualities that helped define Allied victory. Testing, refinement, and devolution on the battlefield. The Sherman's journey from factory blueprint to battlefield powerhouse was shaped by an ongoing cycle of testing, feedback, and iterative engineering. Unlike many tanks of the era that were designed once and used with minimal alteration, the Sherman existed as a constantly evolving platform. Engineers and military evaluators understood that the realities of combat would expose flaws impossible to predict in controlled environments. Because of this, the Sherman program relied heavily on a vast network of testing grounds ranging from the deserts of California to the muddy-proving fields of Aberdeen, where every component of the tank was pushed to failure so that solutions could be engineered before the problems reached soldiers on the front lines. Early testing focused on structural resilience, drivetrain endurance, turret rotation speed, and how the tank performed under prolonged stress. Engineers monitored armored deformation after repeated hits, analyzed stress fractures and suspension components, and measured gearbox temperatures during continuous operation. Each test produced mountains of data that allowed engineers to pinpoint weak points long before they could endanger crews in combat. This approach resulted in a unique engineering culture where rapid refinement was expected and improvements were incorporated almost as soon as frontline reports identified deficiencies. When Sherman crews in North Africa reported issues with ammunition igniting after penetrating hits, engineers responded by developing the now famous wet stowage system, surrounding shells with liquid-filled containers that dramatically reduce fire risks. When tank units encountered difficulty defeating heavier German armor, engineers accelerated development of the 76mm high-velocity gun and redesigned turret elements to accommodate the new weapon. Even the fire control systems underwent continuous refinement with upgraded optics, stabilized sights, and more responsive turret motors introduced as the war progressed. Field modifications created by soldiers also fed directly into the engineering pipeline. Units improvised additional armor by welding spare track, links, and steel plates to their hull solutions that engineers later standardized into formal upgrade packages. Reports of track failures in specific terrains led to changes in rubber composition, while feedback about suspension stress during long marches influenced the transition to the HVSS system rather than resisting field-driven innovation. The Sherman program embraced it, turning battlefield improvisation into factory-produced improvements. The tank's adaptability allowed for the development of mission-specific variants that expanded the Sherman S role across multiple theaters. Engineers created amphibious DD Shermans equipped with flotation screens for beach assaults, mine-clearing Shermans fitted with flails or plows, and flamethrower-equipped models designed for jungle warfare. Recovery vehicles, command tanks, and artillery support versions also emerged, each requiring careful adjustments to weight distribution, cooling systems, and internal architecture. These variants proved the engineering robustness of the Sherman platform. Its frame was strong and flexible enough to accept entirely new purposes without compromising reliability. By the time World War II came to an end, the Sherman had undergone hundreds of refinements, both large and small. More than 49,000 units had been produced across numerous variants, each representing a stage in the tank's evolution. The cumulative effect of these improvements created a machine far more advanced than the early models that first rolled into North Africa. The Sherman's engineering legacy is defined not by its initial specifications, but by its capacity for transformation. It was a tank designed to evolve continuously, adapting to new threats, new terrains, and new technological demands. This culture of relentless refinement turned the Sherman into one of the most successful armored platforms ever built. It was not just a tank, it was an engineering framework capable of growth. Its evolution on the battlefield demonstrated how feedback-driven innovation, flexible design, and scalable manufacturing could together create a weapon system that remained relevant throughout the most intense armored conflict in history. The Sherman's greatest strength was not its armor or firepower, but its ability to become better with every mile driven and every battle fought.